Hello everybody. I have received ABHA Coil for testing. I had it for about 2 weeks now, and before I continue with my asynchronous power measurement, I just want to put some analysis on this coil. I don't have, so the first analysis did already provide some information that you need a specific amplifier and driving stage for this coil. So the frequency or the efficiency of frequency on this coil is very low, between 1 and 5 kilohertz, and the amplifier stage I have here is not, I repeat, is not optimized for that. I have also a single stage only. I have no half bridge. You need also a half bridge for that, so the efficiency is not very high. However, I saw a couple of interesting phenomena I would like to run you through. So in all the cases where you see performance analysis, most of the time so-called LED bulbs are used. I have them as well. I have the stronger one, 7 watt. I could eliminate one as well. However, because of the electronics and because of the amplifier stage I have, which is not optimized for this kind of coil to be used, it is not efficient at all. So what I decided is I used a halogen bulb, a 70 watt halogen bulb. It's more efficient. It is not electronic, so I can drive that and I have a good information about what's going on with you. So what you're going to see is when the bulb is illuminated, but the illumination of the halogen bulb is not that relevant. It gives you some indication. However, bear in mind, high frequency, it is not the best for low resistance load actually to consume power. However, it gives you some indication, and I like to walk you through that. I want to start off with demonstrating that a load to an energy harvesting system or coil system needs to be exactly matched. So what we have here with the ABHA coil is representative for a lot of other energy harvesting systems, which all suffer from the same problems, that the load is in most cases not properly matched. Regardless of the efficiency of this coil system, let's look at the first evidence here. I use a 70 watt halogen bulb, and because my amplifier stage is also not optimized for driving this coil, I will have inefficiency. Regardless of this inefficiency, what I can show and demonstrate is that the load is not matched to the energy of, or to the wave, or to the impedance of the coil system. How can I do that? It's very simple. The way you probably would look at a load or halogen bulb is probably how much light it produces. So that is a very poor way to define if your energy system is creating a lot of energy, because our standard load here is based on 50 Hertz, and that's where it draws the most efficient, well, not efficient, but the most energy from the system. However, all the systems like a halogen bulb and so on, they're very inefficient. They're wasting a lot of energy in heat and so on, and what you generate here in form of light is very poor. So I will not go to that subject, but what I would like to explain and show and demonstrate to you here is that the illumination strength, brightness, is not related to the power, because I haven't done any impedance matching. How can I tell you? Very simple. I will sweep to a couple of frequencies I found being quite strong here on that system. The only thing I have done is that the load is part of the coil, that I have added a microwave capacitor. So what you can see here on the side, that's all peak-to-peak value, is the current value peak to peak. So if you take that off, if you take 50% off, it's a safe bet. So it would be around 100 watt here. I have an input at the moment around 5 watt, and illumination is poor as well. So that is a 70 watt bulb. With 5 watt, it looks about no, I would say it should be brighter than that with 5 watt. But if I go through, you will see that even with a response of frequency, it is not the same. So let me go briefly through a couple of other frequencies. And we go through, so the brightness goes down now at that level. Let's go up to the next brightness. So you see here that is quite independent from, so brightness is coming higher. So if it goes a little bit stronger into the resonance field here, the current and the system drops dramatic. But it's still not a good enough indicator that the energy at that moment is harvested, because it should draw more energy. So that's another indication of such kind of coil systems, that under load the power requirement becomes lower. Let's go down further. Don't want to be focusing too much on frequency. I want to show only the difference between energy harvesting or energy draw from the system in terms of getting the brightness higher, and what actually is in a system available. So going down further, the brightness is increasing a bit, so 2.4 kilohertz. I want to have a little bit more. So the coil is starting to sing. At 2 kilohertz you can hear it. So what I want to do now is to make it a little bit more visible. You see, I'm still under the 200 mark here, peak to peak. So let's say 100 watt, and I'm still around here under 5 watt. Let's go up to 100 volt, because my amplifier stage is very inefficient. I have to give it much more potential in to throw some power out of it. So 100 watt. So the problem you all face is, under such circumstances, so that has not changed here at all. However, the brightness has changed. So the power here at the moment is around 15 watt here, and here let's say 50 watt. So this energy is reflected back to your amplifier, and that is what is destroying your amplifier, because without its impedance match it will destroy your amplifier. Most of you probably have experienced. However, my amplifier is fairly safe. It's not foolproof. I still did kill a couple of under such circumstances. So impedance matching is a necessity, not only from energy harvesting point of view, but also from the point of view that the energy is delivered to the system, not reflected back to the amplifier. Let's go further down. You can hear the coil singing. Current is going down a little bit. Brightness is going up. You see here at that moment here, let's say 1.6, 1.7. Again, that there seems to be an independent wave going through the system. In order to measure that, I would have to measure exactly at the filament in the middle of this bulb to understand what kind of frequency is going through here. Going further down. So when it stops here, you see that I have again a resonance frequency. It has no impact here on the brightness. It has an impact on the coil. So the coil at the moment likes this frequency and produces a steady power output. Going further down. The brightness is higher now. It does not change here. It's also interesting. That gives you another indication that something is completely different going on here. There is no direct relationship between brightness here and power input, and also it has no relation between power generation via the coil system and brightness. That is a very strong indication that impedance matching is not taking place. Go further down. So that is bright 1.1. Of course you have harmonics going on here, so you will have a small up and down of brightness, but not to extent to what I get delivered in here. Look at 1 kilohertz around. I get about 300 watt peak to peak. So if I just take off 50%, that would be 150 watt, and it have 15.5 watts. That has barely changed here. So what it means is that the power injection into the coil system stays steady, but based on the frequency, I have a complete different power generation, or let's say tapping into the energy field around the geometric constellation of this bifilar coil. Go down. That goes now to half of it. Brightness is quite high at the moment. You see here again I dropped and it's running again. Next time it synchronizes again, it will go up, but it will not have any influence on the brightness. Let's have a look. I'm at 900 Hertz now. 123, 170, 200 watt, 220 watt, 250 watt. The closer we go to the original 50 Hertz it will be. I would normally need to add an additional one which shows you the frequency. That the frequency inside the coil is different than the frequency I'm injecting into the coil. So 250, 260 watt here, 2.3 amp. Putting in 15.6 watt at the moment. Further down, let's go down to, let's go down to 500. You see the brightness does not change at all, doesn't matter how I go through here, so it's completely independent. You see a small variation going up and down, but not to a great deal. So that's 500 Hertz, which have been recommended by someone to try that out. The 500 Hertz of course needs to be matched by your coil system. It's not a general requirement to apply 500 Hertz, so I want to make that quite clear here. The coil system need to be adapted to take advantage of the 500 Hertz. That means impedance matching and with the LCR circuit. So that is not taking any advantage here. Go further down. Let's go down to 50 Hertz. Current goes down here to 13 watt. And you see quite little get out here. Let me go down to 50 Hertz. So that would technically mean that you can apply your main voltage. You don't need any kind of amplifier, just put main voltage in it. The worst thing that can happen is that you blow your fuse. But I tell you here, because this coil is not happy with 50 Hertz, what happens here is at 50 Hertz is almost nothing. Nothing happens here. I would go to that extent that I would say actually that I have now the power input and output that's equal. So I have 12 watt here at the moment, and if I say 30 watt here and cut it by 12, I think it's the same amount of energy I have here, and that looks like, yeah, around 20 watt. So at 50 Hertz at mains frequency, that system is not efficient at all. It becomes efficient around 1 kilohertz, but that needs to be adapted for that load. Thank you.